In Part 1 of Lecture 4, we will discuss processes and threads. The discussion so far has presented the concept of a process as embodying two characteristics: resource ownership and scheduling execution. In terms of resource ownership, a process includes a virtual address space to hold the process image. You may recall from Lecture 3 that the process image is the collection of program, data, stack, and attributes defined in the process control block. From time to time, a process may be allocated control or ownership of resources, such as main memory, input-output channels, input-output devices, and files. The operating system performs a protection function to prevent unwanted interference between processes with respect to resources. In terms of scheduling execution, the execution of a process follows an execution path or trace through one or more programs. This execution may be interleaved with that of other processes. Thus, a process has an execution state, running, ready, and so on, and a dispatching priority, and is the entity that is scheduled and dispatched by the operating system. To distinguish the two characteristics, the unit of dispatching is usually referred to as a thread or lightweight process, while the unit of resource ownership is usually referred to as a process or task. Multi-threading refers to the ability of an operating system to support multiple concurrent paths of execution within a single process. The traditional approach of a single thread of execution per process, in which the concept of a thread is not recognized, is referred to as a single-threaded approach. The two arrangements shown on the left-hand half of the figure on the slide are single-threaded approaches. MS-DOS is an example of an operating system that supports a single user process and a single thread. The right half of the figure on this slide depicts multi-threaded approaches. A Java runtime environment is an example of a system of one process with multiple threads. Of interest in this section is the use of multiple processes, each of which supports multiple threads. This approach is taken in Windows, Solaris, and many modern versions of Unix, among others. In this part of the lecture, we give a general description of multi-threading. The details of the Windows, Solaris, and Linux approaches will be discussed later in this lecture. In a multi-threaded environment, a process is defined as the unit of resource allocation and a unit of protection. The following are associated with processes: a virtual address space that holds the process image, protected access to processors, other processes if we are doing inter-process communication, files, and input-output resources such as devices and channels. Within a process, there may be one or more threads, each with the following: a thread execution state, such as running or ready, a saved thread context when not running. One way to view a thread is as an independent program counter operating within a process. An execution stack. Some per-thread static storage for local variables. Access to the memory and resources of its process, shared with all other threads in that process. Figure 4.2 illustrates the distinction between threads and processes from the point of view of process management. In a single-threaded process model, where there is no distinct concept of a thread, the representation of a process includes its process control block and user address space, as well as user and kernel stacks to manage the call-return behavior of the execution of the process. While the process is running, it controls the processor registers. The contents of these registers are saved when the process is not running. In a multi-threaded environment, there is still a single process control block and user address space associated with the process. But now there are separate stacks for each thread, as well as a separate control block for each thread containing register values, priority, and other thread-related state information. Thus, all of the threads of a process share the state and resources of that process. They reside in the same address space and have access to the same data. When one thread alters an item of data in memory, other threads see the results if and when they access that item. If one thread opens a file with read privileges, other threads in the same process can also read from that file. The key benefits of threads derive from the performance implications. First, it takes far less time to create a new thread in an existing process than to create a brand new process. Studies done by the Mac developers show that thread creation is 10 times faster than process creation in Unix. Secondly, it takes less time to terminate a thread than a process. Third, it takes less time to switch between threads within the same process than to switch between processes. Fourth, threads enhance efficiency in communication between different executing programs. In most operating systems, communication between independent processes requires the intervention of the kernel to provide protection and the mechanisms needed for communication. However, because threads within the same process share memory and files, they can communicate with each other without invoking the kernel. Thus, if there is an application or function that should be implemented as a set of related units of execution, it is far more efficient to do so as a collection of threads rather than a collection of separate processes. Listed here are 4 examples of the uses of threads in a single-user multiprocessing system. Foreground and background work. For example, in a spreadsheet, one thread could display menus and read user input, while another thread executes user commands and updates the spreadsheet. This arrangement often increases the perceived speed of the application by allowing the program to prompt for the next command before the previous command is complete. Asynchronous processing. Asynchronous, or elements that are not timed together in the program, can be implemented as threads. For example, as a protection against power failure, one can design a word processor to write its random access memory, or RAM, buffer to disk once every minute. A thread can be created whose sole job is periodic update, and that schedules itself directly with the operating system. There is no need for fancy code in the main program to provide for time checks or to coordinate input and output. Speed of execution. A multi-threaded process can compute one batch of data while reading the next batch from a device. On a multiprocessor system, multiple threads from the same process may be able to execute simultaneously. Thus, even though one thread may be blocked for an input-output operation to read in a batch of data, another thread may be executing simultaneously. Thus, even though one thread may be blocked for an input-output operation to read in a batch of data, another thread may be executing. Lastly, modular program structure. Programs that involve a variety of activities or a variety of sources and destinations of input and output may be easier to design and implement using threads. In an operating system that supports threads, scheduling and dispatching is done on a thread basis. Hence, most of the state information dealing with execution is maintained in thread-level data structures. There are, however, several actions that affect all of the threads in a process, and that the operating system must manage at the process level. For example, suspension involves swapping the address space of one process out of main memory to make room for the address space of another process. Because all threads in a process share the same address space, all threads are suspended at the same time. Similarly, termination of a process terminates all threads within that process. As with processes, the key states for a thread are running, ready, and blocked. Generally, it does not make sense to associate suspended states with threads because such states are process-level concepts. In particular, if a process is swapped out, all of its threads are necessarily swapped out, and because they all share the same address space of the process. There are 4 basic thread operations associated with a change of thread state. Spawn. Typically, when a new process is spawned, a thread for that process is also spawned. Subsequently, a thread within a process may spawn another thread within the same process, providing an instruction pointer and arguments for the new thread. The new thread is provided with its own register context and stack space and placed on the ready queue. Block. When a thread needs to wait for an event, it will block, saving its user registers, program counter, and stack pointers. The process may now turn to the execution of another ready thread in the same or a different process. Unblock. When the event for which a thread is blocked occurs, the thread is moved to the ready queue. Finish. When a thread completes its register context and stacks are deallocated. A significant issue is whether the blocking of a thread results in the blocking of the entire process. In other words, if one thread in a process is blocked, does this prevent the running of any other thread in the same process, even if that other thread is in a ready state? Clearly, some of the flexibility and power of threads is lost if the one blocked thread blocks an entire process. We return to this issue subsequently in our discussion of user-level versus kernel-level threads. But for now, let us consider the performance benefits of threads that do not block an entire process. The figure shown here shows a program that performs 2 remote procedure calls to 2 different hosts to obtain a combined result. In a single-threaded program, the results are obtained in sequence, so the program has to wait for a response from each server in turn. Rewriting the program to use a separate thread for each remote procedure call results in a substantial speedup. Note that if this program operates on a uniprocessor, The requests must be generated sequentially and the results processed in sequence. However, the program waits concurrently for the two replies. On a uniprocessor, multiprogramming enables the interleaving of multiple threads within multiple processes. In the figure shown here, 3 threads in 2 processes are interleaved on the processor. Execution passes from one thread to another, either when the currently running thread is blocked or when its time slice is exhausted.